Alrighty, welcome back everybody to the 13th week of our algorithmic programming course, the Tech Bytes program, where we're solving a new problem each and every day. We're building new concepts, learning about new things, and applying them each and every week. And today's going to be new, different, learning about a new topic, which we have not really touched upon in the past couple of months, seeing what that's all about, and even getting to do an example today. As usual, guys, thanks for coming on in today. We got something special planned for you. So without any further ado, we got to get started off with the thing we've all been anticipating, Quote Wars. You guys know who I am, guys. My name is Rasnikia, senior at James B. Cohen High School, and my quote for today is, commenting your code is like cleaning your bathroom. You never want to do it, but it really does create a more pleasant experience for you and your guests and people who use the bathroom. Now, that's
Thank you for adding that element into this class.
Why did you choose the one with bathroom? You could have chosen like it's cleaning your room as a teenager, and they hate cleaning up their socks.
Apply it to whatever you like, but essentially the idea is the same, right? You're cleaning something, and it's we don't like commenting code because it's extra time. You gotta explain stuff, what's happening, but at the end of the day, it's necessary, right? Because you want to make sure that's clean, organized, and it's something which we've been doing now as a part of product development. Every time we begin a project, we make sure the first week we're going over our steps. Like last week, Labio was going over the steps for our quiz game. We laid out the steps what we're going to do. We do the exact same process every time. And it's so that not only us, but say when we're showing off our project to others and they're looking at our code, they can be like, oh, I know exactly what this function does. So bathroom, house, backyard, say what you want, but the same thing applies.
All right, so today I brought a meme. It says basically just programming on your own. It's like President Biden going up the stairs without falling. But when someone is watching over you, actually programming, whether it's the simplest line of code like print X, you either make some sort of error or some sort of syntax, like you write print wrong or something, but you just make mistakes way more when people are watching you. So that's what this meme says, and I thought it was really funny.
I put my code in the chat.
Okay. You might not think programmers are artists, but programming is an extremely creative profession. It's logic-based creativity. It is actually, because you need a lot of creativity to actually think up of a code that does something your way. Oh yes, let's go. Thank you, Joe.
Yeah, a lot of these I like to be. Avanish, I'll let yours go too. Joe's quote is "Get yeeted, Ayush." That's a pretty good one.
Yeah.
Chasing, I came up with this during chess club because Rishi said I did a lot more moves. I did what I had to do while I could. I did what I had.
What is that?
To survive.
Look, Rishi said there were a lot of moves I did when I did chess, and I said that and thought that would be the perfect quote for this. So you're welcome. You have been blessed by me, the quote master.
Yes, I have gotten Trump today. So it's been a while, but humbling. Alrighty.
My favorite quote is it had to be done. That's one of my favorite quotes.
It had to be done, and it was done.
It's one line.
My favorite quote is replit.
Yes. Perfect.
We're heading off to today. Speaking of today, guys, a quick reminder, we got this month of April 2 more weeks with our regular programs of algorithmic programming, product development, and video gaming hour happening for the last time, I believe, this Friday, or we might be having one more at the end of April, yeah. So catch us there. We're going to keep on working on our project of the quiz game with objects and classes this Wednesday. But for today, let's get to today's new concept and agenda.
Before we do talk about the concept, which I think is very, very interesting, basically we are going to do what we always do, talk about this new concept, which is one of my favorites, and I believe it's among every coder's like top topics that they want to talk about. But we are going through how to basically learn. We're going to learn that topic and then see some examples. We have a problem that we will first whiteboard how to solve, and then finally we'll code it in Replit, which is, I think, Avanish's favorite quote.
Alrighty, so let's get down to today's new idea. That being this thing called recursion. Before me and Lobby say anything about what recursion is, anybody have any guesses? Anything they've heard previously? What is this word recursion?
Is it recurring but without the ing, just with an ion?
Well, Chase, you had me there for the first half. 100% right. It's recurring. It's an idea of doing something multiple times. We're getting there. Anybody else have any ideas? Chase, are we gonna do a virtual Python coding summer camp? So Chase, we will be unveiling our new summer courses in
Like, I think it means like something coming back or doing it again.
Definitely.
Like
Yep.
that re.
Good job. You guys are using the prefix. Yeah, the re. So it's that idea of doing something multiple times. Good. Anybody else have any ideas? Alrighty, well, that is a good start and solid foundation to think about. It's an idea of doing something over and over again, but let's talk a bit more in detail.
All right, so what is recursion? It's, as Rayan said, the word re is very important because we basically will have to recall a function within itself. So basically, think about loops where we call the thing inside it multiple times. But in recursion, we basically call the same function inside it. So imagine, let's see, imagine like a computer inside a computer, inside a computer, inside a computer, inside a computer. It's kind of like that, but it's a function inside a function inside a function, and so on. So basically, why people use recursion is when there are an infinite amount of possibilities that you can go until, and you don't want to use a loop for basically breaking a large problem into smaller chunks and then coding those to eventually solve the overall problem. And then there are two types of recursions: direct and indirect.
Exactly. And you guys don't really know what direct and indirect is, guys. Direct is the idea we'll see when we actually code it out of calling a function inside of itself, and then indirect is calling a different function from inside of one function. So it's that basic idea, like we said, it's breaking down a big problem into a smaller one. Now let's take a look at how that's possible. So this is an example of a recursive function. Ignore the function header, but basically we have a function called recursion. It's taking in a parameter we have of a variable. Now you're probably noticing that we have two main things which are going around when we have a recursive function. Can anybody around the class, what is this called?
It's like an if x is equal to 0. It's not like certain if it's equal to 0.
Yes, so
like a checking operator.
Okay, yeah. So remember, it's called a conditional, and I think Avanish, you were trying to tackle what it means in terms of recursion, and you were right. Sort of that idea of it's something called a base case. Now, a base case is one of the things which makes up a recursive function. A base case is the condition which, because if you think about it, right, we have a recursive function. We're saying that we're going to call that function over and over again. So doesn't that mean if I have a function, I'm calling it infinite number of times? Now, if I call any function infinite amount of times, we're going to get a runtime error and our code is going to lag out. We're going to see a whole essay of red filling up our output box, right? But how do we avoid that when doing this idea of recursion? Well, we'll code this out later as well, but there's something which prevents that from happening called a base case. And that's usually an if-else statement, aka conditional, which makes sure that once we reached a certain condition of our parameter, we are going to return a value. Now, what that allows us to do is that when we're returning that value, it's going to return to the next case. Then the previous time we call that function. Then the previous time we call that function, making sure that we're working up our way on the chain. We'll whiteboard this out later as well, making more sense. But that makes sure that our function hasn't been called an infinite number of times and makes it possible for our program to open and close at the end of the day. So here's that idea once again. We see that the function's name is recursion, but we're calling the function recursion from inside recursion. So calling this function from inside itself. And that's the main idea. And I think we'll talk about it a little bit more.
Yep. So just as Rand said, two main parts basically of any recursive function. You have that base case, which basically tells that function that this is where we want to end calling this function over and over again. So if we want to end when x is equal to 0, just as in the example that we saw, then we just say if x is equal to 0, then instead of calling that function over again, we just say return a value. And then that goes on to the last time that function was called, returns that, and then returns that, and then returns that, goes back to the first time we call that function. And then as as we said before, but the else condition is basically if it's not the base case, suppose I can just annotate over here. Suppose I have my function def, I want to recursive. And then inside I pass in some sort of parameter, then if our base case is if x is equal to 0, then we just want to return nothing. It just tells the function to stop here. We don't want to go to -1, -2, -3. But what if it is, what if we put in 7, so recursive 7, then when it's 7, instead of returning something, we go out of there. I'll just tab in here so we know. Tab. We go out of the conditional, and instead of returning, we call the same function again, recursive. And then instead of x, we just do x minus 1. So when we call recursive, so recursive 7, this will call recursive 6 because
Can't see your screen.
I think you got to click out on the side. There we go. Yep.
Oh, okay. Is that the way it works?
Yeah.
Yeah.
Oh,
you
okay.
gotta click once you.
Okay, that's weird. Okay, sorry about that. But yeah, so over here, I'll just draw this time. This is my function that we just saw in the last screen, and this is the base case. So the last number we want to repeat when recursing through the function. And then this is for every time we go through the function that's not this case. And basically that goes off until we go to 0. And when we do hit 0, it doesn't go to -1, but it just stops and returns everything.
Exactly.
And I will undo that. Okay.
Alrighty. So now with that basic idea of what recursion is, how about we start applying this idea and do an example with it with factorials. Now, I believe we may or may not have talked about factorials in the past, but we can do a quick little example. I do not know if we have. Yeah, okay. So we can do a quick little example of what a factorial is.
I think we have gone over factorials. Yes, Avanish says yes as well.
Okay, yeah. So for those who of us do not know, if you guys don't know, it's totally fine. Say we have a number 3 and then the factorial sign, which is an exclamation mark. 3 factorial. That's a simple multiplication problem for us, telling us that we're going to do 3 times all the numbers preceding it, going up till 1. So 3 times 2 times 1. That gives us 6. Similarly, you can do this for any number. If we have 5 factorial, that gets us 5 times 4 times 3 times 2 times 1, getting us 120.
120.
And I think, so I guess we could, in the spirit of Avanish saying that we already did this, do a quick little speed run right here, just for the fun of it. You guys do like doing those. Chase and Avanish ready to go head to head?
Yes.
Right. So here we go. We'll do 6 factorial.
$720.
Yep.
Dang it.
2 factorial.
2.
2. Dang it.
How about 7 factorial? This is a trick, divided by 6 factorial. So do some division out here.
Hint, hint, it's not that hard.
It looks hard.
It might be a stumper. Amelia saying 1. Good guess, Amelia.
7.
Exactly. And the reason why, guys, you guys don't have to know this, but it's a simple math trick. Since we have 7 factorial, right? We know 7 factorial is equal to 7 times 6 times 5 times 4 times 3, all the numbers before it, right? So 7, it's expanded. It's 7 times 6 factorial, which is essentially the same thing. And doing that divided by 6 factorial, similar terms cancel out. We're left with only 7. So good job, Avanish, getting that out. All right, so it looks like we do have the idea of what factorial is. But today, let's take a look at how we can tackle this problem of factorial with recursion.
Yep. Okay. So what we will need for the for actually coding this, of course, variables. We'll need those variables to contain our numbers that we pass through the function. And also one more thing, we'll need parameters. Parameters are also a type of variable that we pass in through a function. Inside that, I will write that out. So if we have def function, and then inside those parentheses, okay, so inside those parentheses, it's that x that is the parameter, which we will be using today.
Exactly, guys. And we're going to be using a function which is going to use that idea of recursion. A function which will call itself to find the factorial, and we'll have to think about what will the base case be, which makes sure our function is going to be called an infinite number of times, along with the other case going on in the else condition. There we go.
Yep. And as Ryan hinted, we will need an if and else statement because it's that one condition that we need to check every time we run that function, whether that base case is being met or not. If not, then we keep calling that same function over and over again.
Exactly. So now, how about we do a quick little whiteboard and then we'll get to actually coding it out.
Yep. All right. So y'all can see my screen, yes. Okay, so what we did in factorials, let's take 5 factorial because it's just a cool factorial, I think, is 5 times 4 times 3 times 2 times 1. So what's happening over here is we're multiplying a number times one number less than that number, times one number. So 5 times 4 is 5 times, let's just write that down. 5 times 4 is basically 5 times 5 minus 1. And the same thing goes on for these two as well. 4 times 3, 4 times
4 minus
3.
1.
Yeah, exactly. 4 times 3 is equal to 4 times 4 minus 1. Let's just write out the other two as well. 3 times 2 is equal to 3 times, and forgot, yes, 3 times 3 minus 1. And finally, 2 times 1 is equal to 2 times 2 minus 1. So basically, this is the logic that we're going to put inside that function that we're going to keep using over and over again, which makes sense because if you take a look at each of these lines, to actually use a function and reuse that function for this kind of multiplication is kind of weird because we'll need to have 2 variables, 5 and 4. But in here, the only variable that is changing between this and this and this and this is this 5, 4, 3, and 2. And this whole, I guess, 5 minus 1, we can just say x times x minus 1. So the way the function that we are going to create is going to work, remember, it's going to be a recursive function. So I'm going to call it recursive factorial. Now, I'm not going to code all of it in here, just going to show you guys what it looks like. So let's draw this to make it more interesting. So what we went over before, does anyone remember what's one of the two main things that are needed in a recursive function? It starts with a B, two word, I guess, name.
Amelia, great job. Yep.
Oh, okay. Sorry, I was not looking at the chat. Oh, nice. Okay. So yeah, so the first thing is the base case. Okay. Yes.
That was me accidentally.
Okay. Okay, so the base case is when we want to stop. So in this case, when did we stop? When we went from 5 to 4 times 3 times 2. And when did we stop? When x was equal to 1, because after that, so when x is equal to 1, then it's just 1 times, where is it, times 0 is equal to 0. But we don't want to use the 0 because that kind of messes everything else up, because 0 times any number is just 0. And 5 factorial cannot be 0. So we want to stop when our x is equal to 2. And that is what our base case will be. So, oh, there's the highlighter. Okay, so the base case will be stop, or yeah, stop using, you know what, I'm just gonna type. So stop calling the recursive function when the parameter variable is 2 or less than 2, 1, 1. So we still want to use it when it's 2, but when it's 1, we don't. We just want to return 1. All right. So the base case was one part of the two main parts of a recursive function. What's the second part? The most important part. Actually, the second most important part. Yeah, Amelia got it again. So it's the else statement. So if it's not the base case, then what is it? Then we actually have to call the recursive function over and over again. And that's what will happen over here. Let's move this over here. Let's see. All right, okay. Over here, if, okay, so I'm just gonna say else. The if part was if it's a base case, then we stop calling the recursive function and just return 1. Else, what do? We call this same function over again, and instead over here, I'll just draw this in, but we have a parameter of x inside those parentheses. And we use that same parameter and call the same function. So basically say recursive factorial. But instead of putting in x, we're going to put in x minus 1. So what it's going to do is it's going to basically go through the same process with x minus 1. So basically if we call this function recursive, me and my naming conventions for functions are very bad. Okay. Recursive factorial, and suppose we put in 3. Let's put in an easy number for now. This will call, then call recursive
Otherwise, I'm gonna be old fat fart.
Factorial 2, because it we first go to the base case. Since 3 is not equal to 1, then we call this. So that'll call recursive factorial 2, and then recursive factorial 2 will call recursive factorial 1. Okay, 1. And after calling that, we will multiply this x. So after calling the recursive factorial x minus 1, you just multiply it by x. It's the same logic that we had right over here. It's 4 times, 4 times 4 minus 1. So it's x times recursive factorial of x minus 1. So yeah, this calling recursive factorial 3 will in turn call recursive factorial 2, which will call recursive factorial 1, which will return 1. So 1 goes to 2, and it's 2. Oh, that's horrible drawing. So 2. Okay, let me use my mouse. Maybe that'll help. Okay, so 2 times 1. And then this is sent to this, which is just 3 times whatever is sent over here, which is 2 times 1. So 2 times 1. And if we take a look at what Rayan told us, very nice blocks. Factorial is just, so 3 factorial is equal to 3 times 2 times 1. So that's how the recursive function will work. In case it'll call these 3 iterations of the same function, and it'll return 3 iterations, which will kind of sum out to be this. That was a lot of explanation, but you guys will see what it looks like with actual code in Python in Replit.
Alrighty, so speaking of the code, how about we go check it out, how we will tackle this problem. As per the usual, the link
First
to...
one in.
That's okay. Ayush, it was never meant to be. Well, recursion is meant to be, so let's try to apply that today. There's a code link, guys. Hop on to our Replit, and let's get the idea sorted out. So a lot of you did a great job. We got the basic explanation now, right?
Boosts on Replit.
There's boosts.
That's the first thing that popped up when I clicked the link.
It says 8 times the CPU and RAM of the free REPLs.
Oh, wow.
Interesting. All right.
Maybe it's a new update in the homepage.
Maybe on your side. Okay, all right. Well, let's get to today's code and let's get this problem sorted out. Firstly, guys, to get started off, we got the basic idea. I'm going to create our function. We can say define do recursion. We can just call it. And then remember, we're going to have to take in a value. What's that value called? Anybody remind us?
Parameter?
Exactly. We will just call that x. This will be the number which will be passed back into our function. So a lot of you just explained to us what our base case is. And usually in a recursive function, the base case is always the first segment of code, which is found there. So does anybody remember what was our base case when the number we're passing in is equal to?
Is it equal to the itself?
Well, so let's think about it, right? So we got our recursive function. So say we're doing do recursive 5, right? So if actually that's way too big of a number, we'll say we'll make it 3, all right? So say we're doing do recursive 3. What this is going to do is eventually we're going to call do recursive 2, and then we're going to end up calling do recursive 1. Now, once we reach the 1, when the value of 1 is being passed in as a parameter, we have to look for something because that's when we're going to return the value of 1. So what are we looking for our base case?
Do we want to go to 0? Do we want to multiply everything by 0?
No.
Yeah, so when do we stop?
At 1?
1.
Mhm.
Exactly. Yep. So if we, like you said, if we multiply by 0, that's getting rid of all of our work. So that's not the goal. The goal is to make sure that we can actually get a value at the end. So if our variable is equal to 1, then all we have to do is return whatever the number is. In this case, it would be 1. Now, that's the base case. What if the number being passed in isn't 1? What if we're calling the function do recursive and passing in the parameter of the value of 3? Well, then we have to think about what's going to happen in the else condition. So in this case, we're still going to be returning a value from our function, but we have to think about what is a factorial. When I'm saying do recursive 3, what I'm actually saying is, like Labi was doing the expanded notation on the whiteboard, this is actually telling us to do 3 times 3 minus 1 factorial. So all we have to do now is essentially convert that into code. So if we think about it, the value we currently have is the variable x. And then I have to call the function again, but with the -1. So I would do recursion. And then anybody know what I'm going to type in the parentheses?
X.
Anything extra I might need because we're going one behind?
X minus 1.
Exactly, Avanish. Yep. So like we did in the notation right here, we're doing 3 times 2 factorial if we're going to take the factorial of 3. So in this case, pretend x is the number of 3, is number 3, and then this is representing the 3 minus 1 factorial. And then eventually what this will allow us to do, by going back and forth, we will get 3, then times 2, times 1 if we do the factorial of 3, which is equal to 6. So let's try and apply this and see if it works out. Remember, this is our base case, and then this is what happens every time base case is not met. All right, so let's call this function out. So we'll say, let's do the factorial of, how about we do 3? We just did that. We should get 6, right? So here we go. Let's run it. There we go. We get the number 6, and actually what I'm going to do is rename this function to do factorial. I think that's more specific. So you can just replace that function name if you'd like. It's a good idea, organizing our variables and function names. So there we go, it's 6. If we do it similarly, let's go 5 factorial. We should get 120, and there we go, we get 120. And remember, guys, the way this is working is like we just discussed. It's calling do factorial 5, which then calls do factorial 4, which then calls do factorial 3, then do factorial 2, and lastly, the base case of do factorial 1. Once this last piece function has been called, the do factorial 1, we return with the value of 1. So then it becomes 2 times 1.
So when you put 3, how did you get 6 again?
The math or the code?
The code.
Yeah, so if we do the 3 example, so just pretend we're not doing these 5 and 4. If we're doing 3, we're going to call do factorial 2, and then we're going to call do factorial 1. Now, once we pass the value of 1, we're going to reach the base case right here, right? Which is returning number 1. That allows us to go back to this second function and then do 2 times 1. The product of that is 2. And that goes back to the original function call we made, which is just 2 times 3, which gets us 6.
Okay.
This is for sure a new idea, guys. So if you have any questions, please do not feel like you cannot ask. Ask away. This is a new topic. We totally expect you guys to have questions.
Yep.
So this is basically like, it's almost like a calculator, but it goes down 1 every time.
In terms of factorial, yeah, yep, we're decreasing the value by 1 until we reach that important thing called our base case. And if I were not to have this base case, then what would happen, guys, is if this is not here, and I remove this else statement, this function is going to keep on running infinite number of times. And if I hit run, the website will probably crash or something of that sort. Well, yeah, we got the error already, right? It's telling us maximum recursion depth exceeded. That's telling us right there that this function will never end executing.
And so basically, can't we just do like use the if thing, or use like a while loop to do this?
Yeah, we could definitely do a solution using a while loop. But today's main goal was to just show how we can do with recursion and that idea of calling.
We can do like while and then have it like just decrease the x value like over and over until we get to 0.
Yep, we have a, if we pseudocode it out, we got a variable, I'd say, right here. So if you do like a while loop version, we'd have some variable, which is say 5, and then we would run our while loop until our variable is greater than 1. And then in here, we would probably have a variable keeping track of the product. And as we're going through, just decrease the value of x by 1. So this is actually a good discussion you brought up, Ayush. For a lot of recursion problems, there's usually a solution using a for loop or a while loop. But doing a recursion is a more advanced. So it's sort of like, we're talking in English, right? We can talk, there's basically, we can say, oh, this was very good. Or you can say this was super extravagant. Now, the second sentence is much more stronger because of the vocabulary, right? So similarly, in programming, recursion is a much more advanced, nice way of showing that you know how to do cool things. And it shows that you have an advanced vocabulary. So whenever we can use advanced topics, we like to do that.
Yep. Also, recursion lets you do so many more things than actually using for loops or while loops. You just have to know how to handle them, basically. Because the way I just learned recursion is, those bathrooms with mirrors on both sides that reflect each other and go on like forever. That's basically recursion, but with code. But you have to put a stop to it, which is the base case.
Can you do negative numbers?
Yeah, you can, but we'll just have to put the base case as like -1 and do x plus 1 for that.
There we go.
Okay.
And if we were to go an even number, we should be outputted an even value because odd number of negatives gets the final negative, and then even number gets us positive. Cool idea, Chase. Alrighty, well, if you guys have any further questions, ask them away right now, guys. But other than that, this brings us till the end for today's algorithm programming, introducing a new idea of recursion. Hopefully you guys find it interesting. It is for sure advanced. So if you guys have any questions next week, that is totally acceptable. We'll continue to utilize this in our future problems as well. Other than that, guys, this Wednesday, continuing to work on our quiz game. And then Friday, the showdown of Joe versus Chase in Video Gaming Hour. Catch you guys then. Have a good week, guys. See you.
Bye.
And the recursion, can it go